Assalamualaikum, my name is Muhammad Daniel, matrix number 82720, and I will explain on how we solve this question 1. So the question is, calculate the pH at each point listed for the titration of 100 ml of 0.1 mol cocaine. Okay, and then this is the base dissociation constant, 2.6 times 10 to the power of -6 with 0.2 mol acid nitric. The points to calculate are on the given volume of acid 0.0, 10, 20, 25, 30, 40, 49, 49.9, 50, 50.1, 51, and 60 milliliter. And we have to draw a graph of pH versus volume of acid. So this is a titration of 100 milliliter of 0.1 mol cocaine, which is a weak base, with 0.2 mol acid nitric, which is a strong acid. So the data given to us, we have volume of cocaine, which is 0.1 liter, concentration of cocaine 0.1 mol, and then we have the base dissociation constant 2.6 times 10 to the power of -6, and then we have therefore we need to find acid dissociation constant. So how? We need to Kw divided by Kb. So Kw value is always the same, 1.0 times 10 to the power of -14, and then divide by Kb. So we get 3.846 times 10 to the power of -9. So from here we can find the pH for conjugate acid, which is negative log, and then times 3.846 times 10 to the power of -9, and we get 8.41. And the concentration of acid nitric is 0.2 mol. And then for the mol of base is 0.01 moles. So how to calculate? Okay, we need to calculate all of the volume given. So we have 12 volumes we need to do. So how to do it? For the first one, for no acid added, we can just calculate the base concentration. So this is how we do: square root of the dissociation base times with the concentration 0.1 mol, and then we get 0.0001612 mol, and then we can just directly calculate the pH, which is negative log times the concentration, and we get 3.79 as our pH. That's for when no acid added. But when the acid is added, so we need to calculate moles of acid, moles of base remain. So this is how we do: 0.2 times 0.01, 0.2 mol times 0.01, 0.002 moles. And then for the base remaining, we subtract and we get 0.008 moles. And then for the total volume, 100, the initial volume, we plus the acid that we add later, which is 10, and then we get 0.110 liter. So how to find the mole? We can divide the mole with liter, and we got 0.07273 mol for base, and then for acid 0.01818 mol. And then how to find the pH? We can use this this is how we find the pH, which is pKa plus log base divided by acid, mol base and mol acid, and we can get 9.02. And we do it the same for 20 milliliter, 25 milliliter, we do it the same, 30 milliliter also the same, 40, and also 49, and also for 49.9. But for 50 milliliter, which is our equivalent points, we do it differently. On here, all base already neutralized, and then the total volume is 150, which is 100 plus 50, and then we can just calculate the conjugate acid concentration, which is 0.01 divided by 0.15, and we get 0.0667 mole. And yeah, and then we can calculate the ion of H plus. This is how we calculate it. 3.846 times 10 to the power of negative 9 to the 0. Times 0.0667 mole, and then we get 5.06 times 10 to the power of negative 5 mole. And pH we can directly calculate, which is the acid, because all base already neutralized, so we just calculate the acid, and then we get 4.8. For excess acid, which is for more than 50 milliliter, 51 and also 60 milliliter, this is how we do. We calculate the moles of acid, 0.2 times 0.0501, and we get 0.01002 moles. And then we calculate excess acid, 0.01002, subtract 0.010, and we get 0.00002 moles. The total volume is 150.1 milliliter converted to liter. So in this case, we have added more strong acid than needed to neutralize the base. So we now have leftover H plus ions in the solution. So we can ignore the weak conjugate acid because the strong acid dominates. So that's how we find the pH. So that's why we only calculate the H plus ion here. So this is how we calculate it. Okay. And then we get 1.33 times 10 to the power of negative 4 mole, and the pH is negative log, times 1.33 times 10 to the power of negative 4, and we get 3.88. We do the same for all the excess acid for 51 milliliter and also 60 milliliter. Then this is our result. Okay, that's all.
After calculating all the listed acid volumes, we can make the final pH table, where for no acid, the pH is 10.21, 10, 9.02, 20, 8.59, 25, 8.41, 30, 8.24, 40, 7.81, 49, 6.72, 49.9, 5.72, 50, 4.80, 50.1, 3.88, 51, 2.88, and finally 60, 1.90. After that, we can finally make the titration curve, and here is the titration curve based on the table and the calculation that we made earlier, where it shows a typical titration curve of a weak base with a strong acid, including the buffer region and a sharp drop near the equivalence and a strong acidic region after.
Hello, my name is FAHEEM AHMED, and this is my recorded explanation for question 1 of the titration assessment. My student number is 87182. For choosing an indicator, from the graph it can be seen that the equivalence point is around pH 4.8. A suitable indicator for this titration is methyl red, which happens to change color from red to yellow as the pH increases from acidic to alkaline, with a transition range between pH 4.4 and 6.2. This color change occurs within the steep region of the titration curve, which in turn ensures accurate endpoint detection.